this presentation is really on, it's not just controls and systems, it's also tying in motion and finite element analysis. And just to go over the agenda quickly, I'll talk a little bit about, just go over an introduction to control systems. This may be a review for some people. For other people that have never done this type of work, it might be useful. And then I'll talk about our software solutions here at MSC. And then I'll do a demo, a short demo with this landing gear model. And then we'll kind of wrap things up and answer questions. Okay. So this is a slide I kind of stole from one of our training manuals, but I think it's kind of a good slide, especially for people that maybe never worked in this arena. You know, typically we think of analysis, and there's kind of like 4 different levels. You know, you could think of the atomic level, where you got molecular forces and quantum mechanics and all that. And fortunately, we don't have to deal in that realm. And then a kind of a level up from that is this distributed parameter formulation, where we use partial differential equations to solve phenomena that varies over time and space. And so classic examples of that, of course, are finite element analysis and CFD, things like that. And sometimes where people get a little confused with control systems is it's really a level up from that. It's this lump parameter level here, level number 3. So we're using ordinary differential equations, not partial differential equations. And we do study things that vary with time, but these parameters are typically averaged over some area of space. For example, if you think of like a hydraulic actuator, it's got a head end and a rod end. Well, if you got right down to the nuts and bolts of it, the pressure is probably varying a little bit in the head end and the rod end, depending on where you're at spatially. But in the lump parameter method, we assume that those are distinct pressures, and there's one pressure at a given time in each of those volumes. Okay. Another example, of course, is a mass spring system here. It's just a single, all the mass is located in one spot, and you've got a damper and spring forces. And then I guess you could say there's a level above that, which is basically just kind of state models where you're just looking at time delays and algebraic equations. Okay, so let's see if I can get this. Okay, so what do I get from the systems and controls modeling? Well, the output is typically you're interested in some plot of some engineering parameter, like the pressure at a certain point in your circuit, or maybe a flow rate through a valve, or maybe a temperature somewhere as a function of time. So it's kind of performance type analysis. And or maybe you're only interested in the steady state analysis. You don't really care about the transient analysis, like maybe even like an aircraft environmental control system. Maybe only the steady state performance is really important. Or maybe you've got a system that's got feedback control and you want to know if it's stable. Example of that might be like a nose wheel steering system on an aircraft. Something that has a servo valve, and by changing the gain, if you make the gain too high, the system can go unstable. So that's a perfect application for control system analysis. Another nice thing about this level of modeling is that you don't utilize CAD geometry, at least not directly. So that makes it very useful in the early stages of design when CAD geometry is not available, but you really need to hammer down design requirements, like how big does my actuator diameter need to be, how big do my valves need to be, that sort of thing. So that's where it really comes into play, is in the earlier stage when you're setting design requirements. So there's a couple of different ways you can model systems in these type of programs, like I'm going to talk about SimExpert, but they all use a block diagram approach. So let's say we start out with a simple mechanical system that we want to model, like this mass spring system here. If you look, you do a simple force balance on it, you can see that the external force minus the damping and the spring force equals mass times acceleration. So if we wanted to create a block diagram of this model that we would use in a control system package, not just ours, but pretty much every package works this way, what you'd want to do is you'd want to solve for the highest derivative, like I've done here. And then you'd pretty much go from there. So you can see you'd create a summing block right here, and you'd sum in the external force, the damping force, and the spring force, and then you'd multiply that by 1 over m. That's what this 1 over m here is. and that would give you the acceleration. Well, the schematic's not quite done yet because everything's got to be hooked up, right? So what we do here is we'd integrate twice. As you can see here, I've got two integrator blocks. And so after I've got the first derivative, I'd pull off that and multiply it by B and feed it back as the damping force. And then for the spring force, you need to have Kx, right? So now you'd pull off of the second integration operation here. So we're going to have x at this point. You multiply that by k and feed it back. So this is how you would represent a control system in a block diagram. So this is kind of the brute force method. If all you have is a differential equation and you need it solved, this is how you would do it. But there's other ways to do this in our software. Another way you might want to do it is maybe you want to create a block of your own, and you want to do your own calculations behind that block. So you could create a custom code block where you specify what the inputs and the outputs are from the other blocks in the system, and then you write some code around that, basically either in Fortran or in C to calculate the output of that block based on the inputs. And then the third method, if you've got a really complicated system, obviously you're not going to want to write all the differential equations out. So we have libraries that have blocks that include the differential equations behind them. So in fact, we have a block called a single mass block, which is effectively a mass between two hard limits with a spring and a damper. So you could just drag that block onto the circuit and be done with it. And basically all you have to do is specify the mass and these damping and spring constants, and then you'd be done. Okay, so what about applications? Well, we see applications in almost every area of engineering you can imagine. This lists various ones here: powertrain, controls, automotive, flight dynamics, you name it. We've got customers that are modeling these types of systems. And then what happens too, we find often, is that somebody's modeling a plant or some kind of system or controller inside of our solution, like whether it be SimExpert or EZ5. And typically, if they're trying to control something, they want to hook it up to a mechanism, because that's often the case. Is you can think of something like like an active suspension. You'd want to model the mechanical parts in the motion side, but then the hydraulic controls you'd want to model in the system side, and then eventually the idea is if you marry them together so that they're solving at the same time, you'll get a much more accurate solution. Because quite often there's quite a bit of coupling between the dynamics of the two systems, and so you can't really just analyze one side of the system independently without making a bunch of simplifying assumptions that could get you in trouble. Another thing we can do is we can also account for part flexibility on the motion side. So you can think of maybe a part on this ATV here, like maybe the suspension component. Maybe it's important to model the flexibility of that. So we have ways that you could create a finite element representation of that rigid body and then bring that into SimExpert from the structures workspace, and now you're able to tie in both motion, or all three actually, motion, controls, and FEA in one environment. So it's pretty powerful capability that we have here in SimExpert. Okay, so next slide here. So what would be applications that were good candidates for this? Well, basically any type of industry or problem where you've got this coupling of motion and controls. Like I mentioned, an active suspension, could be a missile guidance system, could be like this backhoe here, it could be the hydraulic control of the mechanical backhoe. In manufacturing, there's robots for assembly. In aerospace, you could have a flap system that's driven by a hydraulic control system. So there's really kind of endless the number of applications for this. Okay, so now I think I'll go in and talk a little bit about our software solution, what we offer. So we offer a product called SimExpert, which has been out for a couple of years. And it's really kind of a revolutionary way of looking at analysis. It uses one graphical user interface, SimExpert, but it's got multiple workspaces for doing different types of analysis. So the idea is maybe you bring in this landing gear model, you bring in all the geometry for that, and if you want to do finite element analysis, then you'd work in the structures workspace where you'd see a bunch of menus for meshing, applying boundary conditions and loads and that sort of thing. And then if you wanted to do switch to a motion analysis, you'd switch to the motion workspace, and now you'd see a bunch of menus for things like applying forces, setting up joint constraints, and that sort of thing. And then the one that's a little bit different than the rest of them is the system controls workspace, because it doesn't use geometry like I mentioned. It uses a block diagram approach. But we also have a template builder workspace. Is kind of a block diagram based product, but it's block diagram in the sense that you're not really modeling a system, but you're modeling a flow process. So you could lay out a flow process where you say, I want to take this part, I want to mesh it, then the next step in the flow is I want to apply a boundary condition, and then maybe the next step is I run the analysis, and the next step is I run a motion job. So it's a very powerful way to automate and chain these different types of analyses together. So SimExpert is one unified environment for this end-to-end multidisciplinary simulation. And in the system and controls workspace, I mentioned we have some application libraries to help you out so you don't have to create all these blocks yourself. We have a thermal-hydraulic library, which has pumps and valves, accumulators, actuators, things like that you'd find in a hydraulic system. We also have a gas dynamics library for modeling typically high-pressure pneumatics, compressible flow. Like I think on the F-22, it's got a high-pressure nitrogen missile ejection system. And we have a multi-phase fluid library, which is if you're interested in any type of fluid where it can change its state from vapor to liquid at any point in time. So typically that's used in heating and air conditioning type systems where you've got evaporators and condensers, compressors, things like that. We also have an aerospace vehicle library. This one, there's no charge for this actually. We kind of supply it as is because it's not actively updated or maintained. But if you want to do pretty simple or even fairly complicated aircraft 6-degree of freedom motion, unconstrained motion, and you want to apply turbulence and gust forces and things like that, the aerospace vehicle library is good for that. Okay. So I mentioned EZ5, I think, a few minutes ago. So traditionally, EZ5 has been our standalone package that we've offered for modeling controls and systems. And now what we've done in SimExpert is we've created this new system and controls workspace, which you can pretty much think of as EZ5 inside of SimExpert. But we've added some nice features in here that aren't in EZ5 currently. For example, we've got a model browser, this tree, that's basically a model tree. You're able to run Python scripts and create templates. It's a much more modern interface. We've got an easy way to connect with motion. This INF file, if you've ever hooked up EZ5 and Atoms, you know that you have to generate this INF file, which you don't have to do anymore. There's a spreadsheet tab, which is what's shown over here on the right. So in EZ5, if you wanted to change a parameter like the RPM of a pump or something, you'd have to dive down into that component, double-click it, open up the model editor, and then change the value. Well, in this version of SimExpert, we have basically a spreadsheet tab where you can see all the variables at once and just change the value in that spreadsheet without having to dive into each individual component. So that's kind of a time saver. And then we've also got a new GNU compiler. That's the free compiler that comes with EZ5. It's got some more powerful features than the previous one. So there's quite a bit of nice things here that we've added in the system and controls workspace. And I'll talk briefly about the ways we can hook up motion and controls. I don't want to get into this in too much detail, but there's basically 3 ways you can do it. You can basically have the controller, the control system model. You can have that converted to a DLL, a binary DLL, and then you can link that in with the motion side. That's one way. The advantage of that is you're working from the motion side, so you can see, you can animate the mechanism and everything from the motion side. The two other ways are functional evaluation and co-simulation. These two aren't in the current release of SimExpert, that they will be in SimExpert 2012. And in the functional evaluation, you're actually running the simulation from the system and control side, and you're solving all the equations, both the motion and the controls equations, using the controls package. That's probably the least popular method. And then the third method is co-simulation, where you're passing data back and forth at a fixed time interval, and each program is solving its own equations of motion. So that's what we mean by co-simulation. The advantage of that, it's the most robust method because each program is tuned with its own integrators to solve its own type of problems. Kind of a disadvantage of it is you have to add a communication interval, which adds basically a zero or a hold between those intervals, and if you make the intervals too big, you can start to see your solution deteriorate. So there's advantages and disadvantages to each way. So now I'm going to do this demo of this landing gear model, and you can see that it's got an actuator here. This is what raises and lowers the landing gear, and it's got lock links that go over center and lock into place. So what we're going to do is we're going to have the control system calculate the force that this actuator generates, which is going to be provided to the mechanical model you see here, and then the mechanical model is going to pass back its position and velocity to the control system model. So here's the control system model. It's got a pump with a pressure compensated pump. That's what this map is here. Pumps fluid through a circuit, through a filter, and then it comes to a directional control valve which raises or lowers the landing gear. And there's a signal input on this side to drive that valve. And then the flow goes through a couple orifices back through an accumulator. And here's the actuator that will supply the force to the real actuator, the physical actuator, on the motion side. Okay, so why don't we go ahead and get started with that. So I've got SimExpert open here. Here's the motion model, and I've already got it set up. I can do an animation here, and I'll run this guy, and you can see that the landing gear extends and retracts. So now the way this model is working here is that there's really no force in the actuator that's raising and lowering the gear. It's actually I have an applied motion on one of the links. So it's kind of artificial in that sense. It's basically just a kinematic model where it's got 1 degree of freedom, so I mechanically move one of the links at a certain speed, and that causes the whole thing to come up and retract. So what we want to eventually do is take this model and replace that artificial motion with the actual force that's coming out of the controls model. So now I'll switch over to the System and Controls workspace here. And here's that hydraulic circuit that I showed a minute ago. The idea with when you got one of these block diagrams, each one of these components has a component data table where you go in and you modify it, the different parameters. For example, on this pump, pressure flow characteristic, I'm going to modify that slightly. This is a table that shows the pressure versus the flow output of the pump. The pressure is in bar and the flow is in liters per minute. So I'm going to boost this pressure characteristic up a little bit, so I get a little bit more pressure for a given flow. Okay. And then I could go over to this. This is like I mentioned, this is the block that commands the valve. And I've got a table in here as a function of time that drives the valve. So minus 100 is hard over in one direction, plus 100 is hard over in the other direction. So I'm going to just change the valve command at time equals 1.1 here, and change it to 100, so that I'm basically going to have the valve command one way, then after 1 second I'm going to command it the other way, and then at 3 seconds I'm going to command it back the other way. Okay, so now I've got the standalone model. It's not coupled to motion or anything, so it's always a good idea just to test it to make sure that it works standalone before you try to hook it up to motion. So I've defined a simulation here where I'm going to run this for 6 seconds. And so I can just right-click on this and say execute. And now it will compile the model, and then it will run it, which is what it's doing right now. And then when it's done running, the plotter will come up, and you'll be able to plot any parameter in this model. So, for example, here's a variable that says AX piston AC. Well, what does that mean? Well, the naming convention is, by default, is that the first part of the name tells you what it is. So AX tells me it's a displacement, actuator displacement. The second part of the name, piston, tells me what port it's coming from, because components can have more than one port. And then the third part tells me the name of the component itself. So this is a position coming from a port called piston on component AC. And you can rename these to whatever you want. These are just the default names. So I'm basically plotting out actuator position here. As you can see, it changes in mid-stroke. Okay, so it looks like that model is working fine. And now what we want to do is we want to hook up the motion. So the first thing we need to do is come to this actuator here and change its configuration. So by default, it's a position and velocity output. So by default, it takes in hydraulic pressure, produces a force, calculates the position and velocity. But that's not the way we're going to operate this way. This time, we're going to actually supply position and velocity from atoms, or I'm sorry, from SimExpert Motion, and then that's going to pass back force. So we need to change this to position velocity input. That's the first thing. And then we need to bring out a new component, an interface component, called a motion interface block. Okay, so this is the actual block that represents the mechanical system. And the first thing I want to do is configure that. I'm going to have a couple of inputs and outputs. I'm going to have one input, which is going to be the force, and two outputs, which are going to be the position and the velocity. Now I'll go over to inputs, and I'll just call this one, let's call this one force, SC. And we'll call this one position SC. And we'll call this one velocity SC for system and controls. Okay, so now I just need to hook this up to the rest of the model. First thing I'm going to do here is just throw in a couple of gain blocks. The reason for that is that currently in SimExpert, we haven't got all the workspaces to work together in a system of the same units. Most of the system workspaces I think do, but the controls workspace is working in centimeters, and the motion model is working in millimeters. So what I need to do here is create a conversion from millimeters to meters. So I'm going to put in a scale factor here of 0.1. Like I say, I think in future releases you won't have to go through this step. It should be automatically take care of itself. Okay, let me zoom in a little bit here. So now what I'll do is I'm basically ready to hook this up. So first thing is I click connect, and I click on the actuator, connect to the motion interface. And then a block comes up and tells me what variables you want to pass. I want to pass the piston force to this variable I called force SC, like that. And now I'm going to connect up the position coming out of the motion interface to this gain block. So I want position coming into the input of that gain block. There's the connection, you can see it there. And then I connect the output of the gain block back to the actuator, so the output of the gain block now is connected to AX, which is the actuator position. And then we'll kind of do a similar thing down here for velocity. So we'll connect velocity coming out to the input of that gain block, like you see there. And then we'll connect the output of this gain block back here, where we connect up the output to velocity. Okay, so now you can see the system is set up with the two models connected. Now I mentioned there were three ways to do this. I'm going to use the DLL import method. So I'm basically going to take this model on the hydraulics, export it out as a DLL, and then link that in with the motion side. So the way I would do that is I have to first create what's called an export. So we'll come over here to add new export. Export as motion interface. This just creates the object. I haven't actually generated it yet. So I'm going to have to do the compile right now. I can do that by just right-clicking on that and hitting export. And now that will export the model as a DLL. So it's going to take a second here for it to compile. Okay, so now I'm ready to go back to motion. And remember on the motion side, I had that artificial motion raising and lowering the landing gear. So I want to turn that off. So I come up here to motion, to this retraction motion here. I'm going to say deactivate. And now I've got a force element in here, which represents the actuator force. Right? And it's going to get its value from system and controls. So I'm going to have to activate that one. Okay? And then finally, I need to bring in the DLL. So the way I would do that is I'd go up to SC interface, and I'd select library. A library is another word for a DLL. And then I'll pick the library right here. And you can see it recognize the number of inputs and outputs. So I want to connect up the velocity back through a variable, state variable I defined on the motion side called VEL. And I want to connect up the position to a state variable that I called position, like that. And then on the force side, I need to hook up the force to a state variable that I called force, like that. Okay? So now this is where you keep your fingers crossed and hope that you didn't screw up somewhere along the way. Because we're going to actually run the model now. So we'll come down to the simulation and hit the rerun. We're going to rerun the simulation now. Looks like it's running okay. Okay, so now I can do an animation again. Let's do it. Yeah, let's plot another animation. So we'll go to results, animation. Now it may look the same to you, but I can tell that this is the force-driven one because it's coming up and down quite a bit faster. I kind of went a little bit overkill on the hydraulic force, so it's about 50% faster. Okay, and then the last thing I just want to show real quick is the flex body integration. So let's just pick a part that we want to make flexible. So we'll come down here, and we'll pick this. Let's pick the top, the torque arm. Why don't we pick that? So we'll just make that as the only one visible right now. So I'm going to make this a flexible part. And I want to change this. First of all, I've got to change the rotation center somewhere around there so it rotates nicely. Okay, good. Now, the way this is going to work is, remember there's idealized joints. There's a revolute idealized joint that's located at a point, and there's a spherical joint at the other end, I think it is, that's located at a point. So when we mesh this part, we have to basically spider back rigid body elements, bar elements from the mesh back to the point where the joint is actually located. And to do that, we need to pick load-bearing geometry. So the load-bearing geometry is actually going to be the surface of this pin, right? So we're going to select that as our load-bearing geometry from which to spider out the rigid elements back to the center of the joint. And we'll do something similar on the other side. Okay, so the way we do that now is we go up to Components, and and we'll look at the torque arm top. That's the component we want to work with. So if we double-click that, that brings up this form for that part. And now what I want to do is I want to go to Loads, and you'll notice that I have two joints on this body. I've got the revolute and the spherical, and now it's asking me for load-bearing geometry. So let me do that I'll pick the load-bearing geometry for the first one. I go pick, and I'm going to zoom in here. So the first one we'll pick is, let me zoom in a little more, is this surface, okay? And then we'll pick this surface here. Okay. So now back and I see I picked those two faces as the load-bearing geometry. Now I'm going to go to the other end. And I'll pick the center of that hole to be the load-bearing geometry. Like that. Now I got my load-bearing geometry defined. And now the last step in the demo, really the last thing I got to do is go over to the Structures tab. And this is where it tells the Structures workspace how to create the flexible body. So I have to give it a typical element size. So we'll say 20 millimeters. And we're using quadratic elements. We're going to carry 10 modes. And we hit the Automate button. And then create a flexible part. Now it's switching over to the Structures workspace, where it's going to mesh the part. It's going to run a modal analysis to capture the natural frequencies and mode shapes. Because in the motion side, we're going to represent this body in modal space. The reason for that is just to reduce the number of degrees of freedom. So it does require, so there is an assumption that your model is linear. And it's still working here, but in a second it should switch back to motion. So really what this is doing is it's running the modal analysis, and then it's also writing out what's called a modal neutral file, which contains all the mode shapes and natural frequencies. And that's what the actual motion workspace works with. Okay, so you can see now I'm back in motion. And let's just make every part visible here. And so now you can see that this part is now a meshed part. Now this is kind of a trivial example, I guess, because this part really doesn't have any loads on it. But let's just run the analysis. And so what I can do now is I can just go back to simulation here and rerun that simulation again. Okay, so now if I want to animate that, go to animation, hit the go button, and you can see that now, if you look down here, you can see that the part is actually meshed there. There's really not much deformation going on here because it's just, like I said, it's not loaded. Let me see if I can get this out of the way here and I can zoom in a little bit. So that's really it. That's how you would integrate a motion, structures, and controls model in SimExpert. So let me just go back now to the PowerPoint briefly. Go to a summary. So really this kind of the main takeaways from this, if you forget everything else, is that sometimes high accuracy requires modeling the coupled physics between motion and controls and maybe even finite element analysis. And we have the ability in SimExpert to couple all those in one environment. And we offer the flexibility into controls. I really didn't talk about this much, but you can use either our system controls workspace or you can use MATLAB Simulink, since I know there's a lot of users out there that use MATLAB Simulink. Okay, so with that, I think I'll turn it back to Srinivas.